I want you to do something very simple. I want you to close your eyes. Take a deep breath in. Hold it for just a moment. And now, let it go. Let everything go. The worries of today, the plans for tomorrow, the noise of the world outside your window. None of that matters right now. Right now, in this very moment, it is just you and the universe. And the universe, my friend, has the most incredible story to tell you. A story so vast, so ancient, so quietly beautiful, that by the time we reach the end of it, you will have drifted into the deepest, most peaceful sleep you have had in a very long time. This is a story about everything. About where we came from. About the stars that burn millions of miles away. About the silent darkness between galaxies. About the astronauts who floated weightless above our world and came back, changed forever. About the mysteries that the smartest minds on Earth still cannot solve. And about the future. A future where humans might walk on other planets, build cities among the stars, and reach places we can barely imagine tonight. But here's what makes this story special. I am going to tell it to you slowly. Very slowly. There is no rush. There is nowhere you need to be. There is nothing you need to do. Just listen. Let the words wash over you like waves on a quiet shore. Let your breathing slow down. Let your muscles relax. Let your mind wander into the cosmos. And if at some point you fall asleep, that is perfectly fine. That is exactly what is supposed to happen. The universe will still be here when you wake up. Before we begin our journey, let me ask you a few questions. You do not need to answer them. Just let them float through your mind like clouds drifting across a night sky. Have you ever wondered what existed before the universe was born? Was there darkness? Was there silence? Was there anything at all? Have you ever looked up at the night sky and wondered if someone on a distant planet is looking back at you right now, wondering the same thing? Have you ever thought about what it would feel like to float in space, weightless, with the entire Earth glowing blue and white beneath you? Have you ever wondered why astronauts who go to space come back and say it changed their lives forever? That they saw something up there that words cannot describe? Have you ever thought about what happens to your body in space? How your bones change? How your heart changes shape? How you actually grow taller when there is no gravity pulling you down? Have you ever wondered how far the universe stretches and whether it has an edge? And if it does, what is on the other side? These are the kinds of questions we are going to explore tonight. Not with complicated equations or technical jargon, but with simple, gentle words. Like a conversation between friends on a quiet night. And along the way, I promise you, there will be moments that will fill you with wonder. Moments that will make you see our little planet and your own life in a completely different light. Moments that might just change the way you think about everything. So settle in, get comfortable, pull your blanket a little closer, and let us begin at the very beginning. Not the beginning of human history, not the beginning of Earth, but the very beginning of everything. The beginning of time itself. Now, if you enjoy this kind of content, if you like falling asleep to calm, deep explorations of the universe, then do me a small favor. Subscribe to this channel, press that little bell icon, and leave me a comment telling me what space question keeps you awake at night. I read every single comment, and your question might become the next video. But for now, let us leave the world behind and drift into the cosmos together. Imagine, if you can, absolute nothingness. Not darkness, because darkness is something. Not silence, because silence implies that there could be sound. Not empty space, because space itself did not exist yet. Try to imagine a state where there is no up, no down, no left, no right, no time ticking forward, no matter, no energy, no laws of physics. Nothing. This is what scientists believe existed, or rather did not exist, before the universe was born. And I know that is an almost impossible thing to wrap your mind around. How can there be nothing? How can there be no time? How can there be no space? Our brains evolved to understand the world around us. The trees, the rivers, the sky, the ground beneath our feet. We did not evolve to understand nothingness. But that is where our story begins, in a state that is beyond human comprehension, a state that even the greatest physicists in history have struggled to describe. But here is where it gets fascinating. Even in that state of apparent nothingness, something was happening. Or rather, something had the potential to happen. You see, in the strange world of quantum physics, the world of the very, very small, there is a principle that says true nothingness is actually impossible. Even in what we call a perfect vacuum, a space with absolutely nothing in it, tiny fluctuations are constantly occurring. Pairs of particles pop into existence for the briefest imaginable instant and then disappear again. They are called virtual particles. They appear and vanish so quickly that you could never detect them directly, but their effects are real and measurable. Scientists have confirmed this in laboratories. The vacuum of space is not truly empty. It is a seething, bubbling ocean of potential, with particles winking in and out of reality billions of times every second. Now take that idea and stretch it back to the very beginning. Some physicists believe that our entire universe may have begun as one of these quantum fluctuations. A tiny bubble of energy that, instead of disappearing back into the void like all the others, somehow survived, somehow grew, somehow became everything. Everything you see around you tonight. The walls of your room, the device you are listening to, the air filling your lungs, the ground beneath your building, the oceans, the mountains, the clouds, the moon, the sun, the stars, the galaxies stretching billions of light years in every direction. All of it may have begun as a fluctuation smaller than an atom, lasting less than a trillionth of a second. That is both the most humbling and the most extraordinary idea in all of science. This event, this moment of creation, is what we call the Big Bang. But I want you to forget whatever image just popped into your mind, because almost everyone imagines it wrong. When most people hear the words Big Bang, they picture an explosion, a massive, fiery, dramatic explosion, like a bomb going off in the middle of empty space, sending debris flying outward in all directions. But that is not what happened. Not even close. There was no space for an explosion to happen in. There was no outside for debris to fly into. The Big Bang was not an explosion in space. It was an expansion of space itself. Let me try to explain this in a way that might make sense as you lie there in the dark. Imagine the surface of a balloon, a very tiny, deflated balloon. Now imagine that the entire universe, everything that exists, is on the surface of that balloon. Not inside it, on the surface. Now imagine that balloon begins to inflate. As it inflates, every point on the surface moves away from every other point. There is no center of the expansion. No single point where the bang happened. The expansion is happening everywhere on the surface, all at once. That is closer to what the Big Bang actually was. The fabric of space itself began to stretch, and as it stretched, everything within it began to move apart. Now, in the very first instant of the Big Bang, and when I say instant, I mean a span of time so short that it makes a billionth of a second seem like an eternity. The universe went through a series of phases that are almost impossible to describe in everyday language. But I will try, because they are beautiful in their own way, and understanding them will give you a sense of just how extraordinary it is that you exist at all. In the very first sliver of time, a period that physicists call the Planck epoch, the universe was so unimaginably hot and dense that all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. We do not have the physics to describe this state. Our equations break down. Our theories collapse. It is as if the universe, in its very first breath, existed in a state that is beyond the reach of human mathematics. And that, in itself, is a kind of mystery that should fill you with awe. There are things about the birth of reality that reality itself will not let us understand. As the universe expanded and cooled, and we are still talking about the first tiny fraction of a second here, these forces began to separate. Gravity split off first, becoming its own force. Then the strong nuclear force separated. Then, electromagnetism and the weak force went their own ways. Each separation was accompanied by a phase transition, somewhat like water freezing into ice or boiling into steam, but on a cosmic scale. And with each transition, the universe changed fundamentally. New rules emerged. New possibilities opened up. During one of these transitions, something extraordinary happened. The universe went through a period of incredibly rapid expansion called inflation. In a span of time that lasted far less than a blink of an eye, the universe expanded by a factor that is difficult to express without scientific notation. Imagine taking something smaller than a proton and stretching it to the size of a grapefruit in a fraction of a second. That is the kind of expansion we are talking about. And it happened faster than the speed of light, which might sound impossible. But remember, it was not objects moving through space faster than light. It was space itself stretching. And there is no speed limit on the stretching of space. This period of inflation solved several puzzles about the universe that had been bothering scientists for decades. It explained why the universe looks roughly the same in every direction, because everything we can see was once packed into a tiny region and inflated together. It explained why the universe appears to be geometrically flat, like a piece of paper rather than curved like a sphere. And it planted the seeds for everything that would come later. Tiny quantum fluctuations, random variations in the density of energy, were stretched during inflation from the subatomic scale to the cosmic scale. These fluctuations, these tiny ripples in the fabric of reality, would eventually become galaxies, stars, planets, and you. Take a moment to breathe that in. The atoms in your body, the oxygen filling your lungs right now, the carbon in your cells, the iron in your blood, all of it traces back to those quantum fluctuations in the first fraction of a second of existence. You are, in the most literal and scientific sense, a child of the Big Bang, a direct descendant of that first moment of creation. As the universe continued to expand and cool, it went through more changes. For the first few minutes, the temperature was still hot enough for nuclear fusion to occur everywhere in the universe, not just inside stars. Protons and neutrons, the building blocks of atomic nuclei, smashed together and fused into the nuclei of the simplest elements. Hydrogen, the simplest of all, with just one proton. Helium, with 2 protons and 2 neutrons. Tiny amounts of lithium, the third element. And that was it. Nothing heavier. The universe was not yet old enough or cool enough to create carbon, or oxygen, or iron or gold. Those would come much later, and the way they would be created is one of the most beautiful stories in all of science. But we will get to that. For the next 380,000 years, give or take, the universe was a hot, dense fog. It was filled with a plasma of charged particles, protons and electrons zipping around at tremendous speeds, and photons, particles of light, bouncing off them constantly. Light could not travel very far before hitting a charged particle and being scattered in a random direction. If you could somehow have been there, you would have seen nothing. Not darkness, exactly, but a brilliant, opaque glow in every direction, like being inside a cloud of pure light with no way to see through it. But then, 380,000 years after the Big Bang, the universe cooled enough for something magical to happen. The electrons, which had been flying around freely, slowed down enough to be captured by the protons. They came together to form the first atoms, neutral hydrogen atoms. And suddenly, the photons had nothing to bounce off of. For the first time in the history of the universe, light could travel freely through space. The fog cleared. The universe became transparent. Those photons, released in that moment 380,000 years after the Big Bang, are still traveling through space today. They have been traveling for almost 13.8 billion years, and we can detect them. We call them the cosmic microwave background, or CMB, and they represent the oldest light in the universe, the very first light that was ever set free. When scientists point their instruments at the CMB, they are looking at a baby picture of the universe, a snapshot of what everything looked like when the cosmos was less than 400,000 years old. And what they see is beautiful. A gentle, almost uniform glow of microwave radiation, with tiny, tiny variations in temperature. Those variations, mere 100,000ths of a degree, are the imprint of those quantum fluctuations from the first instant of creation. They are the seeds that would grow into galaxies and galaxy clusters, and the vast cosmic web of structure that fills the universe today. After the CMB was released, the universe entered a period that scientists call the Dark Ages. And for good reason. Although light could now travel freely, there were no sources of light. No stars had formed yet. The universe was filled with hydrogen and helium gas, slowly cooling, slowly expanding, slowly being pulled together by gravity in the regions where the density was just slightly higher than average. For millions of years, the universe was dark. Completely, utterly dark. Not the kind of dark you experience when you close your eyes, because, even then, there is the faint glow of light through your eyelids. This was a darkness more complete than anything you have ever experienced. A darkness that stretched across billions of light years, the entire universe, waiting in silence for the first stars to be born. And then, after perhaps 100 to 200 million years of darkness, gravity finally won its slow battle. In the densest regions of gas, where those primordial quantum fluctuations had left their mark, clouds of hydrogen and helium began to collapse under their own weight. As the gas compressed, it heated up, hotter and hotter, denser and denser, until, at the core of these collapsing clouds, the temperature reached about 10 million degrees. And at that temperature, something extraordinary happened. Hydrogen atoms, squeezed together with unimaginable force, began to fuse. Their nuclei merged, releasing enormous amounts of energy. Nuclear fusion ignited, and the first star in the history of the universe began to shine. Imagine that moment. After hundreds of millions of years of total darkness, a single point of light appears. Then another. then another. Across the universe, in scattered pockets of dense gas, the first generation of stars flickered to life. These first stars, which astronomers call population 3 stars, were unlike any stars that exist today. They were enormous, hundreds of times more massive than our Sun, and because they were made entirely of hydrogen and helium, with none of the heavier elements that moderate the burning of modern stars, they burned incredibly hot and incredibly fast. Their surfaces blazed blue-white with a ferocity that we can barely imagine. And their lives were short. While our Sun will burn steadily for about 10 billion years, these first stars exhausted their fuel in just a few million years. A cosmic blink. But in their brief, brilliant lives, and especially in their spectacular deaths, these first stars did something that would change the universe forever. Deep in their cores, under the crushing pressure of their own gravity, they forged the first heavy elements. Through a chain of nuclear fusion reactions, hydrogen was fused into helium, helium into carbon, carbon into oxygen, oxygen into neon, neon into silicon, and silicon into iron. These were the first carbon atoms in the universe, the first oxygen atoms, the first iron atoms, elements that had never existed before, elements that would one day become the building blocks of planets, of oceans, of living things. And when these massive first stars died, they did not go quietly. They exploded in supernovae of unimaginable power, blasts so energetic that for a brief moment, a single dying star could outshine an entire galaxy of hundreds of billions of stars. And in the fury of those explosions, in the extreme temperatures and pressures generated by a collapsing stellar core, even heavier elements were forged. Gold, platinum, uranium, elements that can only be created in the most violent events the universe has ever known. These elements were blasted out into space, mixing with the surrounding gas, enriching it, seeding it with the raw materials for the next generation of stars. There is a famous quote by the astronomer Carl Sagan. He said, "We are made of star stuff." And he was not being poetic or metaphorical. He was stating a literal, scientific fact. Every atom of carbon in your body was forged in the nuclear furnace at the heart of a star that died billions of years ago. Every atom of oxygen you are breathing right now was created in a stellar explosion. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, all of it was manufactured inside stars and scattered across space when those stars died. You are, quite literally, made of recycled stardust, and so is everything around you. Your bed, your pillow, the floor beneath you, the entire earth. All of it is stardust, rearranged by billions of years of cosmic evolution into the familiar forms you see today. Knowing this, how can you not feel a deep, quiet connection to the universe? You are not separate from the cosmos. You are part of it. A piece of the universe that has somehow become aware of itself, lying in the dark, listening to its own story. Now, as the first generation of stars lived and died and enriched the cosmos with heavier elements, the universe continued to evolve. Gravity continued to pull matter together. The slight over-densities left behind by the quantum fluctuations of the Big Bang grew larger and larger as more matter fell into them. Clouds of gas merged into bigger clouds. Groups of stars formed small clusters. Clusters merged into larger structures. And over hundreds of millions of years, the first galaxies began to take shape. A galaxy is an almost inconceivably vast collection of stars, gas, dust, and dark matter, all bound together by gravity and orbiting around a common center. The smallest galaxies contain a few billion stars. The largest contains several trillion. And the universe contains at least 2 trillion galaxies, spread across a volume of observable space that stretches about 93 billion light-years from one side to the other. Those numbers are so large that they have almost lost their meaning. But try for just a moment to let them sink in. 2 trillion galaxies, each containing billions or trillions of stars, each star potentially orbited by planets. The sheer scale of the universe is one of those facts that, once you truly grasp it, changes the way you see everything. Our own galaxy, the Milky Way, is a barred spiral galaxy about 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars, and at its center lurks a supermassive black hole called Sagittarius A star, which has a mass about 4 million times that of our Sun. Our Sun is just one ordinary star among those hundreds of billions, located about 26,000 light-years from the galactic center, in a relatively quiet suburban arm of the spiral. And our planet is just one small rocky world, orbiting that one ordinary star. When you look up at the night sky and see the faint milky band of light stretching across the heavens, you are looking at the disk of our galaxy edge on. Every individual star you can see with your naked eye is within our galaxy. The vast majority of them are within a few thousand light-years of us, and beyond them, in every direction, stretch billions of other galaxies, each with their own hundreds of billions of stars, most of them too far away and too faint for your eyes to see. Let that thought accompany you as you breathe slowly, in and out. You are lying on a planet that is spinning at about 1,000 miles per hour at the equator. That planet is orbiting the Sun at about 67,000 miles per hour. The Sun is orbiting the center of the Milky Way at about 500,000 miles per hour, and the Milky Way itself is hurtling through space at about 1.3 million miles per hour, pulled by the gravitational attraction of galaxy clusters millions of light-years away. You are moving, right now, at tremendous speed through the cosmos, and yet you feel perfectly still, perfectly calm, perfectly at rest. There is something deeply soothing about that contradiction. You are racing through the universe, and yet here, in your bed, everything is quiet and peaceful. Now, let us bring our attention a little closer to home. Let us take a slow, gentle tour of our own solar system, because the neighborhood we live in is full of wonders that many people never learn about, and each planet, each moon, each asteroid has a story to tell. It all began about 4.6 billion years ago, in a cloud of gas and dust floating in the Milky Way. This cloud was the remnant of previous generations of stars that had lived and died, so it was enriched with all those heavy elements that stellar nucleosynthesis and supernovae had produced. Something disturbed this cloud. Perhaps a shockwave from a nearby supernova. Perhaps the gravitational tug of a passing star. Whatever the cause, the cloud began to collapse under its own gravity. As it collapsed, it began to spin, flattening into a disc shape, like a pizza maker spinning dough. At the center, where the density and temperature were highest, the proto-sun began to form, and in the disk around it, the planets would soon begin to take shape. The process of planet formation is called accretion. In the disk of gas and dust around the young sun, tiny grains of material began to collide and stick together. Over millions of years, these grains grew into pebbles, pebbles into boulders, boulders into planetesimals miles across, and planetesimals into protoplanets hundreds or thousands of miles across. Closer to the sun, where temperatures were high, only rock and metal could remain solid, So the inner planets, Mercury, Venus, Earth, and Mars, formed as small, dense, rocky worlds, further from the sun, where temperatures were low enough for ices to exist, water ice, methane ice, ammonia ice. The building material was more abundant, and the protoplanets grew much larger, large enough to gravitationally capture huge amounts of hydrogen and helium gas from the surrounding disk. This is how Jupiter and Saturn became gas giants, and how Uranus and Neptune became ice giants. Let us visit each of these worlds now, one by one, slowly, as if we are drifting through the solar system in a spaceship with no particular hurry to be anywhere. Mercury is the closest planet to the Sun, orbiting at an average distance of about 36 million miles. It is a small world, only slightly larger than our moon, and it has a barren, cratered surface that looks remarkably like the lunar landscape. But Mercury holds some surprises. Despite being the closest planet to the Sun, it is not the hottest. That distinction belongs to Venus, for reasons we will discover shortly. Mercury has almost no atmosphere. Just the thinnest trace of atoms blasted off its surface by the solar wind. Without an atmosphere to distribute heat or trap it, Mercury experiences the most extreme temperature swings of any planet in the solar system. On the sunlit side, temperatures soar to about 430 degrees Celsius, hot enough to melt lead. On the dark side, temperatures plummet to about -180 degrees Celsius. The difference between the hottest and coldest points on Mercury is over 600 degrees. And here is something few people know. Mercury is shrinking. Over the past 4 billion years, as its iron core has slowly cooled, the planet has contracted, and its surface has wrinkled like the skin of a drying apple. Long, winding cliffs called scarps crisscross the surface, some of them hundreds of miles long, carved by the slow contraction of an entire world. Now let us drift a little further from the Sun, to Venus. Venus is almost exactly the same size as Earth. It has a similar mass, a similar composition, and for a long time, scientists speculated that it might be a lot like our planet, a twin world. But when we finally got close enough to study it, we discovered that Venus is about as different from Earth as a planet could possibly be. Venus is the hottest planet in the solar system, with surface temperatures averaging about 465 degrees Celsius, hotter than Mercury, even though Venus is nearly twice as far from the Sun. The reason is Venus's atmosphere. It is incredibly thick, about 90 times the pressure of Earth's atmosphere at sea level, and it is composed almost entirely of carbon dioxide, a greenhouse gas. This creates a runaway greenhouse effect, where heat from the sun is trapped so efficiently that the surface temperature climbs and climbs until it reaches a hellish equilibrium. The clouds on Venus are made of sulfuric acid, and it rains sulfuric acid, although the drops evaporate before they reach the surface because it is simply too hot. And here is one of the most thought-provoking things about Venus. There is evidence that it may not always have been this way. Some climate models suggest that Venus may have had liquid water on its surface for billions of years. It may have had oceans. It may have been habitable. But at some point, something went catastrophically wrong. Perhaps volcanic activity released too much carbon dioxide. Perhaps the oceans evaporated, and the water vapor, also a powerful greenhouse gas, pushed the planet past a tipping point. Whatever happened, Venus went from a potentially habitable world to the most hostile planet in the inner solar system. And that story, the story of a world that lost its habitability, carries a quiet but important lesson for those of us living on Earth. There is another strange fact about Venus that I find oddly soothing. Venus rotates backwards. If you could stand on the surface of Venus and somehow survive the temperature and pressure, you would see the sun rise in the west and set in the east. And Venus rotates so slowly that a single day on Venus, one complete rotation on its axis, takes about 243 Earth days. But a year on Venus, one complete orbit around the sun, takes only about 225 Earth days. So a day on Venus is actually longer than its year. Think about that for a moment. It is the kind of fact that makes you smile and then makes you sleepy because of how delightfully absurd the universe can be. Now, let us come home. To Earth. Our beautiful, fragile, one-of-a-kind, the third rock from the sun. And as far as we know, the only place in the entire universe where life exists. Although, as we will discuss later, that may not be true for much longer. Earth sits in what astronomers call the habitable zone, sometimes called the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, like Venus. Not too cold, like Mars. Just right. And liquid water, as far as we know, is essential for life as we understand it. Water is the universal solvent. It facilitates the chemical reactions that life depends on. It fills our cells, transports nutrients, regulates temperature. Without liquid water, life as we know it could not exist. But being in the habitable zone alone is not enough. Earth has several other features that make it uniquely suited for life. It has a strong magnetic field, generated by the churning of its molten iron core. This magnetic field creates an invisible shield around the planet that deflects most of the harmful charged particles streaming out from the sun, the solar wind. Without this magnetic shield, the solar wind would gradually strip away our atmosphere, much as it has done on Mars. Earth also has plate tectonics, the slow movement of giant rocky plates across the surface of the planet. This might seem unrelated to life, but plate tectonics plays a crucial role in regulating our climate over long timescales by recycling carbon between the atmosphere and the Earth's interior. And Earth has a large moon, which stabilizes the tilt of our axis, giving us relatively stable seasons. Without the moon, Earth's axial tilt would wander chaotically, potentially causing extreme climate fluctuations that might make complex life impossible. And here is something that might give you perspective as you lie there tonight. The atmosphere that keeps you alive, the thin layer of gas that separates you from the lethal vacuum of space, is astonishingly thin. If Earth were the size of a basketball, the atmosphere would be thinner than a sheet of paper wrapped around it. Everything you have ever known, every person who has ever lived, every breath anyone has ever taken, has occurred within that razor-thin layer of gas, clinging to a ball of rock hurtling through the void. It is enough to make you want to take a deep breath and savor it. Let us continue our journey outward now, to Mars, the red planet. Named after the Roman god of war because of its blood-red color, which comes from iron oxide, rust, on its surface. Mars is a cold, dry, dusty world today, with a thin atmosphere that is mostly carbon dioxide and surface temperatures averaging about -60 degrees Celsius. But Mars was not always this way. Billions of years ago, Mars was a very different place. It had a thicker atmosphere. It had liquid water flowing on its surface. We can see the evidence today. River valleys, carved by flowing water, stretch for hundreds of miles across the Martian surface. Lake beds and deltas, where rivers once emptied into standing bodies of water, have been photographed by orbiting spacecraft. Mineral deposits that can only form in the presence of liquid water have been detected by rovers on the surface. Mars was once warm and wet. It may even have been habitable. So what happened? Where did the water go? Where did the atmosphere go? The answer lies in Mars's core. Unlike Earth, Mars does not have a global magnetic field. It lost its magnetic field early in its history, probably because its smaller core cooled and solidified, shutting down the dynamo that generates a magnetic field. Without that magnetic shield, the solar wind was free to pound the Martian atmosphere relentlessly, stripping it away molecule by molecule over hundreds of millions of years. As the atmosphere thinned, the surface pressure dropped, and liquid water could no longer exist on the surface. It either evaporated into space, froze into the ground as permafrost, or was locked into the polar ice caps. Mars went from a warm, wet world to a cold, dry desert. And some of its water may still be there, frozen beneath the surface, waiting for future explorers to find it. Mars also holds the record for the tallest volcano in the solar system. Olympus Mons rises about 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. Its base is so wide that if you stood at its edge, you would not be able to see the summit because it would be beyond the curve of the horizon. Mars also has the largest canyon system in the solar system, Valles Marineris, which stretches about 4,000 kilometers across the Martian surface, roughly the width of the continental United States. If you placed Valles Marineris on Earth, it would stretch from New York to Los Angeles. Several robotic explorers are currently studying Mars. The Curiosity rover has been exploring Gale Crater since 2012, drilling into rocks, analyzing soil, and sending back stunning photographs. The Perseverance rover, which landed in Jezero Crater in 2021, is collecting rock samples that will eventually be returned to Earth for detailed analysis. And Perseverance brought a friend. Ingenuity, a small helicopter drone, became the first aircraft to achieve powered, controlled flight on another planet. Think about that. We flew a helicopter on Mars, on a planet with an atmosphere that is only about 1% the density of Earth's. That is an engineering achievement that should fill you with quiet pride in what humanity can accomplish. Now let us venture further out, past the asteroid belt, that ring of rocky debris between Mars and Jupiter, and into the realm of the giant planets. And as we cross into the outer solar system, everything changes. The planets here are nothing like the rocky worlds we have just visited. They are enormous. They are mostly made of gas and ice, and they are surrounded by systems of rings and moons that are worlds unto themselves. Jupiter is the king of the planets, the largest planet in our solar system by an enormous margin. If you could hollow out Jupiter, you could fit over 1,300 Earths inside it. It has a mass 2.5 times greater than all the other planets combined. Jupiter is mostly made of hydrogen and helium, the same elements that make up the Sun, and if it had been about 80 times more massive, it would have ignited nuclear fusion in its core and become a star. A failed star, you might say. Or perhaps a planet with ambitions above its station. The most famous feature on Jupiter is the Great Red Spot, a massive storm that has been raging in Jupiter's atmosphere for at least 350 years, and possibly much longer. The Great Red Spot is so large that you could fit the entire Earth inside it with room to spare. It is an anticyclonic storm, with winds circling at hundreds of miles per hour, and its deep red color comes from complex chemical reactions in the upper atmosphere. Though scientists are still debating exactly which chemicals produce that distinctive hue. But perhaps the most exciting thing about Jupiter is not Jupiter itself, but its moons. Jupiter has at least 95 known moons, and several of them are fascinating worlds in their own right. The four largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo Galilei in 1610 using one of the first telescopes, and they are collectively known as the Galilean moons. Io is the most volcanically active body in the solar system. Its surface is covered with hundreds of active volcanoes, some of them shooting plumes of sulfur and sulfur dioxide hundreds of kilometers into space. Io's volcanism is driven by tidal heating. Jupiter's immense gravity, along with the gravitational pulls of the other Galilean moons, flexes and squeezes Io's interior, generating enormous amounts of heat. But it is Europa that has captured the imagination of astrobiologists more than any other moon in the solar system. Europa is covered in a shell of ice, smooth and cracked, with very few impact craters, suggesting that the surface is geologically young and constantly being resurfaced. Beneath that ice shell, scientists are now confident, lies a global ocean of liquid salt water, an ocean that contains more water than all the oceans on Earth combined. And where there is liquid water, there is the possibility of life. Deep beneath Europa's ice, in the dark waters of an alien ocean, warmed by tidal heating from Jupiter, there might be hydrothermal vents on the ocean floor, similar to the hydrothermal vents on Earth's ocean floors that support thriving ecosystems of life, without any sunlight at all. We do not know if there is life in Europa's ocean, but the possibility is tantalizing enough that NASA is planning a mission, called Europa Clipper, to study this moon in unprecedented detail. Ganymede is the largest moon in the solar system, larger even than the planet Mercury, and the only moon known to have its own magnetic field. Callisto, the outermost of the four Galilean moons, is one of the most heavily cratered objects in the solar system, its ancient surface a record of billions of years of bombardment. Jupiter also serves as a kind of cosmic guardian for the inner solar system. Its massive gravitational field acts like a shield, deflecting or capturing many of the comets and asteroids that might otherwise plunge into the inner solar system and potentially strike Earth. Some scientists believe that without Jupiter's protective influence, the rate of catastrophic impacts on Earth would be much higher, and complex life might never have had the chance to evolve. So in a very real sense, you might owe your existence to a giant ball of gas 500 million miles away. There is something wonderful about that. Let us drift further now, to Saturn, the jewel of the solar system. Even people who have no interest in astronomy tend to gasp when they see a good photograph of Saturn. Those rings. Those magnificent, impossible, gorgeous rings. They make Saturn arguably the most beautiful object in the solar system. Saturn's rings are made of billions upon billions of individual pieces of ice and rock, ranging in size from tiny grains of dust to boulders the size of houses. The ring system extends hundreds of thousands of kilometers from Saturn's surface, and yet it is astonishingly thin. In some places, the rings are only about 10 meters thick. If you scaled the rings down so that they were a kilometer in diameter, they would be thinner than a razor blade. They are essentially a flat disk of orbiting debris, so thin that when seen edge-on from Earth, they almost disappear. How did Saturn get its rings? Scientists are still debating this. One theory suggests that the rings are the remnants of a moon that ventured too close to Saturn and was torn apart by tidal forces. Another suggests they are leftover material from the formation of the solar system that never coalesced into a moon. And there is evidence that the rings might be surprisingly young, perhaps only 100 to 200 million years old. If that is true, then the dinosaurs lived in a universe where Saturn had no rings. And in a few 100 million years, the rings might be gone, gradually losing material and fading away. We are living in a special time, cosmically speaking, when Saturn happens to have its rings. And that thought, that we are witnesses to a temporary cosmic ornament, is the kind of thing I find deeply moving. Saturn also has a remarkable collection of moons. The largest, Titan, is the second largest moon in the solar system and the only moon with a thick atmosphere. Titan's atmosphere is mostly nitrogen, like Earth's. But its surface conditions are wildly different. The temperature on Titan's surface is about -179 degrees Celsius. So cold that water ice is as hard as rock. But here is what makes Titan truly extraordinary. It has lakes and seas, not of water, but of liquid methane and ethane. Titan is the only body in the solar system besides Earth known to have stable bodies of liquid on its surface. The Huygens probe, which landed on Titan in 2005, sent back images of a landscape with rounded pebbles and drainage channels carved by flowing liquid methane. It rains on Titan. Methane rain, falling from hydrocarbon clouds into methane rivers that flow into methane seas. Some scientists have even speculated about the possibility of exotic, methane-based life on Titan. Life so different from anything on Earth that we might not even recognize it as life. Then there is Enceladus, a small, ice-covered moon of Saturn that has become one of the most exciting targets in the search for extraterrestrial life. The Cassini spacecraft discovered that Enceladus has geysers at its south pole, jets of water vapor and ice particles shooting hundreds of kilometers into space. These geysers are powered by a subsurface ocean, kept liquid by tidal heating. And when Cassini flew through the plumes and analyzed their composition, it found water, salt, organic molecules, and molecular hydrogen. The hydrogen is particularly exciting because it could be produced by hydrothermal reactions between hot rock and water on the ocean floor. On Earth, hydrothermal vents that produce hydrogen support communities of microorganisms called methanogens, which derive energy from the reaction of hydrogen with carbon dioxide. Everything we have found at Enceladus suggests that it has the ingredients for life: the water, the energy, the chemistry. Whether life actually exists, there is a question that a future mission might answer. And it is the kind of question that could change everything we know about our place in the universe. Let us continue outward now, into the colder, darker reaches of the solar system, to Uranus and Neptune, the ice giants. These worlds are less well known than Jupiter and Saturn, partly because they are so far away, and partly because we have only visited them once when the Voyager 2 spacecraft flew past them in the 1980s. But they are fascinating worlds with their own mysteries. Uranus is tilted on its side. Its axis of rotation is tilted about 98 degrees relative to its orbital plane, meaning it essentially rolls around the sun like a ball, with one pole pointed roughly toward the sun for half its orbit, and the other pole pointed toward the sun for the other half. This gives Uranus the most extreme seasons of any planet. Each pole gets about 42 years of continuous sunlight, followed by 42 years of continuous darkness. Scientists are not entirely sure what caused this extreme tilt, but the leading theory is that Uranus was struck by a large object, perhaps an Earth-sized protoplanet, early in the solar system's history, knocking it onto its side. Uranus is classified as an ice giant because, unlike Jupiter and Saturn, which are mostly hydrogen and helium, Uranus has a significant proportion of heavier elements, including water, methane, and ammonia, in the form of high-pressure ices deep within its interior. Its pale blue-green color comes from methane in its upper atmosphere, which absorbs red light and reflects blue and green. Neptune, the most distant planet in our solar system, is a world of storms and wind. It has the fastest winds of any planet, with gusts reaching up to 2,100 kilometers per hour. When Voyager 2 flew past Neptune in 1989, it photographed a massive storm called the Great Dark Spot, similar in appearance to Jupiter's Great Red Spot, but even larger relative to the size of the planet. Subsequent observations showed that the Great Dark Spot had disappeared, only to be replaced by new storms. Neptune's deep blue color, more vivid than Uranus's, also comes from methane. But there may be additional unknown compounds that contribute to its particularly rich hue. Neptune's largest moon, Triton, is one of the strangest moons in the solar system. It orbits Neptune in the opposite direction to Neptune's rotation, what astronomers call a retrograde orbit, which strongly suggests that Triton was not born alongside Neptune, but was captured from the Kuiper Belt, the vast ring of icy bodies beyond Neptune's orbit. Triton has a thin atmosphere and active geysers that shoot nitrogen gas and dark particles several kilometers above its surface, and it is slowly spiraling inward toward Neptune. In a few billion years, Triton will cross the Roche limit, the distance at which Neptune's tidal forces will tear it apart, and Neptune will gain a spectacular ring system, perhaps rivaling Saturn's. Beyond Neptune, we enter the Kuiper Belt, a vast donut-shaped region of icy bodies that extends from about 30 to 50 astronomical units from the Sun. This is the realm of Pluto, once considered the 9th planet but now classified as a dwarf planet. Pluto was demoted in 2006 by the International Astronomical Union, a decision that remains controversial and that many people find surprisingly emotional. We had grown up with 9 planets. Losing one felt like losing a family member. But the New Horizons mission, which flew past Pluto in July 2015, showed us that Pluto is far more interesting as a dwarf planet than it ever was as a planet. The images sent back by New Horizons revealed a world of stunning complexity and beauty. A heart-shaped glacier of frozen nitrogen, informally named Tombaugh Regio after the astronomer who discovered Pluto. Towering mountains of water ice. Smooth plains that appear to be geologically young. Possible cryovolcanoes. Volcanoes that erupt ice instead of lava. Pluto turned out to be a dynamic, geologically active world, far from the cold dead ice ball that most people had assumed it to be. And beyond the Kuiper Belt lies the Oort cloud, a theoretical spherical shell of icy objects that extends perhaps halfway to the nearest star. The Oort cloud is thought to be the source of long-period comets. Those comets that take thousands or millions of years to complete a single orbit around the Sun. No spacecraft has ever visited the Oort cloud, and no telescope has ever directly observed it. It remains one of the most remote and mysterious regions of our solar system. Now, let your mind drift back from the outer reaches of the solar system, back toward home, back toward Earth, and let us spend some time talking about something deeply fascinating and directly relevant to your health and well-being. Let us talk about what happens to the human body in space. Because when humans leave Earth and venture into the weightlessness of orbit, their bodies begin to change in ways that are both surprising and profound. And understanding these changes can teach us a great deal about how our bodies work here on the ground, and even about how to stay healthy as we age. The most obvious change in space is the absence of gravity, or more precisely, the experience of microgravity. On the International Space Station, astronauts and everything around them are in constant free fall around the Earth. They are falling toward the Earth continuously, But because the station is also moving sideways so fast, it keeps missing, tracing a circular orbit. The result is that everything inside the station floats. There is no up or down, no weight pressing on your bones or muscles. And while this sounds delightful, and astronauts do report that floating is one of the most joyful experiences of their lives, it comes with serious consequences for the human body. Let us start with your bones. On Earth, your skeleton bears the constant load of your body weight. Every step you take, every time you stand up, sit down, or lift something, your bones are under stress. And this stress is essential for bone health. Bones are living tissue, constantly being broken down and rebuilt. When bones are under regular stress, the body builds them up. When that stress is removed, the body begins to break them down. This is exactly what happens in space. Without gravity, the mechanical loading on the skeleton drops to almost zero, and astronauts begin to lose bone density at a rate of about 1 to 2% per month. That might not sound like much, but consider that an elderly person with osteoporosis on Earth typically loses about 1 to 2% per year. Astronauts in space are losing bone at roughly 12 times the rate of someone with osteoporosis. In a 6-month mission on the International Space Station, an astronaut can lose as much bone density as a postmenopausal woman loses in an entire decade. And the bone loss occurs primarily in the weight-bearing bones, the pelvis, the spine, and the legs, the bones that would normally be under the most stress from gravity. This bone loss is one of the most significant health challenges facing long-duration spaceflight. A mission to Mars, which would involve at least 7 months of travel each way, plus time on the surface, could result in severe bone loss if countermeasures are not effective. Astronauts on the ISS already spend about 2.5 hours every day exercising, using specially designed resistance machines and treadmills that are equipped with bungee cords and harnesses to simulate some of the loading that gravity would normally provide. These exercises slow the rate of bone loss, but do not completely prevent it. And once astronauts return to Earth, it can take years for their bones to fully recover. Some studies suggest that the bone density of certain astronauts never fully returns to pre-flight levels. Understanding how bone loss occurs in space has actually helped researchers develop better treatments for osteoporosis on Earth, making this one of many cases where space research has direct benefits for people who will never leave the planet. Now let us talk about your muscles. Your muscles, like your bones, need regular use to stay healthy. On Earth, even simple activities like standing and walking require constant muscular effort to resist gravity. In space, these muscles have almost nothing to do. Without gravity pulling you down, you do not need your leg muscles to stand. You do not need your back muscles to hold yourself upright. You do not need your postural muscles to maintain balance. And so, predictably, these muscles begin to atrophy. Astronauts can lose up to 20% of their muscle mass in as little as 5 to 11 days in space, and if they do not exercise rigorously, the loss continues throughout their mission. The muscles most affected are the ones you use to resist gravity on Earth: the calves, the quadriceps, the muscles along the spine. Astronauts returning from long missions sometimes describe their legs as feeling like wet noodles, barely able to support their weight in Earth's gravity. This is sometimes called bird leg syndrome, because the legs lose mass while the upper body, which gets more use in microgravity because astronauts use their arms to push themselves around the station, retains more of its muscle. The exercise regimen on the ISS is designed to combat both bone and muscle loss. Astronauts use a device called the Advanced Resistive Exercise Device, or ARED. which uses vacuum cylinders to simulate weightlifting in microgravity. They can do squats, deadlifts, bench presses, and other exercises against resistance loads equivalent to several hundred pounds. They also run on treadmills and cycle on stationary bikes, all while strapped down to prevent themselves from floating away. This exercise program has been significantly improved over the years, and studies of astronauts on recent long-duration missions show that muscle loss can be largely prevented with diligent exercise. But the bone loss issue remains more stubborn. Your heart also changes in space, in ways that are both fascinating and a little concerning. On Earth, your heart spends its entire life pumping blood against the force of gravity. Blood in your lower body has to be pushed upward against gravity to return to the heart. Your cardiovascular system has evolved with this challenge, and a significant portion of your heart's workload goes toward overcoming gravity's effect on blood circulation. In space, that challenge disappears. Without gravity pulling blood toward your feet, blood redistributes toward your head and upper body. Astronauts in the first hours and days of spaceflight experience a noticeable shift of fluid toward their head, causing a puffy, congested feeling in the face, like having a permanent head cold. Their faces look swollen, their nasal passages feel blocked, and their legs appear thinner than usual. Astronauts have nicknamed this phenomenon puffy face, chicken legs. Over time, the body adapts to this new distribution of fluid. It senses that there is too much fluid in the upper body and triggers mechanisms to reduce total blood volume. Astronauts lose about 10 to 15% of their blood volume in the first few days of spaceflight. The heart, facing less resistance and pumping less blood, begins to decondition. It does not need to work as hard, so, like any muscle that is underused, it begins to weaken and even change shape. Studies using ultrasound on the ISS have shown that astronauts' hearts become more spherical in space, losing some of the elongated shape they have on Earth. And the heart rate and blood pressure regulation systems, accustomed to constant adjustments for gravity, begin to lose their fine-tuning. This is why astronauts returning to Earth often experience orthostatic intolerance, a difficulty in maintaining blood pressure when standing up, which can cause dizziness or fainting. Their cardiovascular systems have to readjust to pumping blood against gravity again. Part 2. One of the most concerning and least understood health effects of spaceflight involves the eyes. It is called Spaceflight-Associated Neuroocular Syndrome, or SANS. During long-duration missions, many astronauts experience changes in their vision. Some become farsighted. Some develop structural changes in their eyes that can be detected on medical scans. The backs of their eyeballs can flatten slightly, and the optic nerve can swell. The leading theory is that the upward fluid shift in microgravity increases the pressure of cerebrospinal fluid around the brain, which in turn presses on the back of the eyes and the optic nerve. But the exact mechanism is still not fully understood, and SANS is considered one of the top health risks for long-duration missions. Some astronauts have returned from the ISS needing glasses when they had perfect vision before they went up, and in some cases, the changes persist long after they return to Earth. Radiation is another major health concern in space. Here on Earth, we are protected from most cosmic radiation by two shields. The first is Earth's magnetic field, which deflects charged particles from the sun and from deep space. The second is the atmosphere, which absorbs much of the radiation that makes it past the magnetic field. In space, both of these shields are gone. Astronauts on the ISS, which orbits within the inner magnetosphere, still receive some protection from Earth's magnetic field. but they are exposed to significantly more radiation than people on the ground. On a mission to Mars, astronauts would spend months in deep space, completely outside the protection of Earth's magnetic field, exposed to two types of radiation that are particularly dangerous: solar particle events. Intense bursts of energetic particles from the sun during solar flares and coronal mass ejections can deliver a large dose of radiation in a short time. And galactic cosmic rays, extremely high-energy particles that come from outside our solar system, from supernovae and other energetic events across the galaxy, are a constant background. These galactic cosmic rays are particularly insidious because they are so energetic that they are extremely difficult to shield against. They can penetrate the walls of spacecraft, the bodies of astronauts, and even the nuclei of individual cells, causing damage to DNA that can lead to mutations and potentially cancer. NASA estimates that a round trip to Mars with current technology would expose astronauts to a radiation dose roughly equivalent to about 1,000 chest X-rays. This significantly increases the lifetime risk of cancer, and NASA has strict career dose limits for astronauts. Developing better radiation shielding and better medical countermeasures is one of the key challenges that must be solved before humans can safely travel to Mars. Sleep is another area where space takes a toll. On the International Space Station, the sun rises and sets about every 45 minutes, resulting in 16 sunrises and 16 sunsets every 24 hours. This wreaks havoc on the circadian rhythm, the internal biological clock that regulates sleep and wakefulness based on light and dark cycles. Astronauts on the ISS use artificial lighting schedules, eye masks, and sometimes melatonin supplements to try to maintain a normal sleep-wake cycle, but many report difficulty sleeping. Studies have shown that astronauts on the ISS average about 6 hours of sleep per night, compared to the 7 to 8 hours recommended for adults on Earth. And the quality of that sleep is often poor, with more awakenings and less deep sleep. This chronic sleep deprivation can affect cognitive function, mood, and immune health. The psychological effects of spaceflight are equally important and equally fascinating. Astronauts on the ISS are confined in a small, noisy, isolated environment for months at a time, with a small group of people who they may not have chosen as companions. They are separated from their families, their friends, their normal routines, and the entire natural world. They cannot step outside for fresh air. They cannot go for a walk in a park. They cannot feel rain on their face or grass under their feet. This kind of isolation and confinement can take a significant psychological toll. And managing the mental health of astronauts is a critical part of mission planning. But there is a positive psychological effect of spaceflight that is so powerful and so consistent that it has been given its own name. It is called the overview effect. Astronauts who see the Earth from space, a small, fragile, breathtakingly beautiful blue marble hanging in the void, almost universally describe it as a profoundly life-changing experience. They describe a sudden, overwhelming awareness of the unity and fragility of life on Earth. National borders become invisible. Conflicts seem petty. The thin, luminous atmosphere looks like a precious, delicate thing that must be protected. Many astronauts have said that the overview effect fundamentally changed their perspective on life, making them more environmentally conscious, more compassionate, and more aware of the preciousness of our planet. Astronaut Edgar Mitchell, who walked on the moon during the Apollo 14 mission, described the experience by saying that he suddenly saw the planet, the stars, the cosmos as an interconnected whole, and that the sense of separate nations and separate peoples dissolved. You want to grab a politician by the scruff of the neck, he said, and drag him 250,000 miles out and say, "Look at that." There is one more delightful effect of spaceflight on the body that I want to mention before we move on. In space, without gravity compressing your spine, the discs between your vertebrae expand. The result is that astronauts actually grow taller in space, typically by about 1 to 2 inches. Astronaut Scott Kelly, who spent nearly a year on the ISS, grew about 2 inches during his mission. Unfortunately, this growth is temporary, and astronauts return to their normal height within a day or two of returning to Earth as gravity compresses their spines again. And the expansion of the spinal discs in space can actually cause back pain, which many astronauts report, especially in the early days of a mission. But the fact that we grow taller in space is one of those wonderful, slightly whimsical facts that makes the universe feel like a place full of surprises. The immune system also behaves strangely in space. Studies have shown that the immune function of astronauts is altered during spaceflight. Some aspects of the immune system become suppressed, while others become overactive. This creates a paradoxical situation where astronauts are simultaneously more vulnerable to infections and more prone to autoimmune-like responses, such as rashes and hypersensitivities. Even more strangely, dormant viruses in the body can reactivate during spaceflight. Many astronauts have experienced reactivation of latent herpes viruses, including the varicella zoster virus, which causes chickenpox and shingles, and the Epstein-Barr virus. The stress of spaceflight, the disrupted sleep, the radiation exposure, and the altered immune function all seem to contribute to this. Understanding how the immune system changes in space is not just important for astronaut health. It also provides insights into how immune function changes with age and stress on Earth, which has implications for treating immune-related diseases in the general population. Now, take a deep breath. We have been talking about what space does to the human body, and some of it might sound a little alarming, but I want to reassure you. The human body is remarkably resilient. Astronauts who spend months in space return to Earth and, with proper rehabilitation, recover most of their pre-flight fitness. And everything we learn about the effects of spaceflight helps us develop better countermeasures, not just for astronauts, but for people on Earth dealing with similar health challenges. The bone loss research has improved osteoporosis treatments. The cardiovascular studies have improved our understanding of heart disease. The sleep research has led to better strategies for managing circadian rhythm disorders. And the psychological insights have informed the treatment of isolation, confinement, and depression in everything from Antarctic research stations to submarine crews to people living through pandemics. Space is not just about exploration. It is about understanding ourselves better. Let us now turn the page of our story and drift back through time. Let us talk about the history of space exploration. How we went from looking up at the stars and wondering what they were, to actually going there. This is one of the greatest adventure stories ever told, and I am going to tell it to you slowly, with all the twists and turns and moments of triumph and tragedy that make it so compelling. The dream of space travel is as old as human civilization. Ancient myths are full of stories about gods and heroes who journey to the heavens. But the idea that humans could actually reach space through technology rather than mythology began to take shape in the early 20th century, thanks to a handful of visionary scientists and engineers. Konstantin Tsiolkovsky was a Russian schoolteacher who, in 1903, published a groundbreaking paper describing the mathematics of rocket propulsion. He derived the fundamental equation of spaceflight, now called the Tsiolkovsky rocket equation, which describes the relationship between a rocket's velocity, the velocity of its exhaust, and the ratio of its initial and final masses. He proposed the use of liquid-fueled rockets, multi-stage rockets, and even space stations in orbit around the Earth. All of this at a time when the Wright brothers had not yet flown their first airplane. Tsiolkovsky never built a rocket himself. He was a theorist, a dreamer. But his ideas laid the mathematical foundation for everything that would follow. Robert Goddard was an American physicist who turned Tsiolkovsky's theories into reality. On March 16, 1926, in Auburn, Massachusetts, Goddard launched the world's first liquid-fueled rocket. It flew for about 2.5 seconds, reached an altitude of about 12 meters, and traveled about 56 meters. It was not much, by modern standards. But it was the proof of concept. Liquid-fueled rockets worked. And they could, in principle, be scaled up to reach much greater altitudes, much greater speeds, even space. Goddard continued his research for years, developing increasingly sophisticated rockets. But he was largely ridiculed by the press and ignored by the American military establishment. The New York Times published an editorial mocking him, saying that a rocket could not work in the vacuum of space because there was nothing for the exhaust to push against. This, of course, was a fundamental misunderstanding of Newton's third law of motion, and the Times eventually published a correction, though not until 1969, the day after Apollo 11 landed on the moon. In Germany, Hermann Oberth published a book in 1923 that independently arrived at many of the same conclusions as Tsiolkovsky and inspired a generation of young German rocket enthusiasts. Among them was a teenager named Wernher von Braun, who would become one of the most important and controversial figures in the history of space exploration. Von Braun became the technical director of the German rocket program during World War II, developing the V-2 rocket, the world's first long-range ballistic missile, which was used to bomb London and other Allied cities. The V-2 was built using forced labor from concentration camps, and thousands of prisoners died in the factories. After the war, von Braun surrendered to the Americans and was brought to the United States along with many of his colleagues and a cache of V-2 rockets as part of a secret program called Operation Paperclip. In the United States, he went on to become the chief architect of the Saturn V rocket, the rocket that would carry humans to the moon. Von Braun's brilliance as an engineer is beyond dispute. But his moral legacy is deeply complicated, and it is important to acknowledge that complexity honestly. The space race, the intense competition between the United States and the Soviet Union to achieve dominance in space, began in earnest on October 4, 1957, when the Soviet Union launched Sputnik, the first artificial satellite. Sputnik was a small, polished metal sphere, about the size of a beach ball, with 4 trailing antennas. It did nothing particularly sophisticated. It simply orbited the Earth, emitting a steady beep, beep, beep that could be picked up by radio receivers on the ground. But the psychological impact of Sputnik was enormous. The realization that the Soviet Union had the technology to put an object into orbit, and by extension, the technology to deliver a nuclear warhead to any point on the globe, sent shockwaves through the American public and government. The space race had begun. The United States scrambled to catch up. In January 1958, the Army Ballistic Missile Agency, with von Braun at the helm, launched Explorer 1, the first American satellite. Explorer 1 carried scientific instruments that made an important discovery: the existence of the Van Allen radiation belts, zones of charged particles trapped by Earth's magnetic field. This was the first scientific discovery made from space, and it set the precedent for the idea that space exploration was not just about national prestige. but about expanding human knowledge. But the Soviet Union continued to rack up firsts. In September 1959, Luna 2 became the first human-made object to reach the surface of the Moon. In October 1959, Luna 3 transmitted the first photographs of the far side of the Moon, the side that always faces away from Earth, which no human had ever seen. And then, on April 12, 1961, came the moment that changed everything. Yuri Gagarin, a 27-year-old Soviet cosmonaut with an infectious smile and a peasant background that made him a propaganda dream for the Soviet government, became the first human being to travel to space. His spacecraft, Vostok 1, carried him on a single orbit of the Earth, lasting 108 minutes. Gagarin had no control over the spacecraft. It was fully automated, because the Soviet engineers were not sure how a human mind would function in the weightlessness of space. They worried that zero gravity might cause disorientation, confusion, or even madness. So Gagarin was essentially a passenger, sealed inside a spherical capsule hurtling around the planet at nearly 28,000 kilometers per hour. But what Gagarin saw through the small porthole of his spacecraft changed him, and the world, forever. He saw the Earth from above for the first time. The blue of the oceans, the brown and green of the continents, the swirling white of the clouds, all against the black velvet of space. He described it as beautiful. He noted that the Earth had a distinctly blue halo when viewed from orbit. He became, in that moment, the first human being to see our planet from outside, to see it whole, to see it as it truly is, a single, beautiful, fragile world hanging in an infinite void. When Gagarin returned to Earth, he was an instant global celebrity. He toured the world, greeted by cheering crowds everywhere he went. He had become a symbol of what humanity could achieve. Tragically, Gagarin died in a jet training accident in 1968, at the age of 34. But his legacy endures. April 12 is still celebrated internationally as Yuri's Night, a celebration of human spaceflight. The United States, stung by the Soviet achievement, responded quickly. On May 5, 1961, just 23 days after Gagarin's flight, Alan Shepard became the first American in space, on a suborbital flight lasting about 15 minutes. Shepard's flight was followed in February 1962 by John Glenn's orbital mission aboard Friendship 7, making Glenn the first American to orbit the Earth. Glenn circled the planet 3 times, and during his re-entry, a sensor indicated that his heat shield might be loose. If the heat shield failed, Glenn would burn up in the atmosphere. Ground controllers agonized over whether to tell him. They decided to have him perform a modified re-entry procedure that might help keep the heat shield in place. Glenn made it home safely. The sensor had been faulty. But the tension of that mission reminded everyone that spaceflight was still an incredibly dangerous endeavor. It was in this context that President John F. Kennedy made one of the boldest promises in the history of exploration. On May 25, 1961, speaking before a joint session of Congress, Kennedy declared that the United States should commit itself to achieving the goal, before the decade was out, of landing a man on the Moon and returning him safely to the Earth. It was an audacious goal. At the time Kennedy made his speech, the United States had accumulated a grand total of about 15 minutes of human spaceflight experience. The technology needed to reach the Moon did not yet exist. The rocket had not been designed. The spacecraft had not been conceived. The navigation techniques had not been developed. Kennedy was essentially telling the nation to do the impossible, and to do it within 9 years. And they did. The program that would take Americans to the Moon was called Apollo. But before Apollo, there was Gemini. The Gemini program, consisting of 10 crewed missions between 1965 and 1966, was designed to develop and test the skills and technologies needed for the moon missions. Gemini astronauts practiced spacewalking, which is exiting the spacecraft and moving around in the vacuum of space, tethered only by a cord. They practiced rendezvous and docking, the delicate art of bringing two spacecraft together in orbit and connecting them. And they practiced long-duration spaceflight, with one Gemini mission lasting nearly 14 days, long enough to prove that astronauts could survive the duration of a moon mission. The Apollo program itself began with tragedy. On January 27, 1967, during a routine test on the launch pad, a fire broke out inside the Apollo 1 command module. The cabin was pressurized with pure oxygen, which is extremely flammable, and the fire spread with explosive speed. Astronauts Gus Grissom, Ed White, and Roger Chaffee were killed. The hatch, which opened inward and required multiple steps to open, could not be opened in time. The 3 astronauts died within 30 seconds. The nation was devastated. NASA was shaken to its core. The accident led to a complete redesign of the command module, including a new hatch that opened outward and could be opened in seconds, a switch from pure oxygen to a mixed atmosphere, and the removal of flammable materials from the cabin. The lessons learned from the Apollo 1 fire, lessons paid for with 3 lives, made every subsequent mission safer. After months of investigation and redesign, the Apollo program resumed. Apollo 7 tested the redesigned command module in Earth orbit. Apollo 8, in December 1968, went further than any human had ever gone before. It carried astronauts Frank Borman, Jim Lovell, and William Anders on a journey around the moon. They did not land. They orbited the moon 10 times, becoming the first human beings to see the far side of the moon with their own eyes, the first to see the Earth from the distance of the moon, and the first to experience the profound isolation of being further from home than anyone had ever been. It was during Apollo 8 that one of the most famous photographs in history was taken. As the spacecraft came around from behind the moon on one of its orbits, astronaut William Anders looked out the window and saw the Earth rising above the lunar horizon, a small, blue, luminous sphere against the infinite black of space. He scrambled for his camera and took the photograph that would become known as Earthrise. That single image is credited with helping to launch the modern environmental movement. For the first time, humans saw their planet as a finite, beautiful, fragile world, with no visible borders, no visible boundaries, just a small oasis of life in the cosmic desert. Anders later said, "We came all this way to explore the moon, and the most important thing is that we discovered the Earth." Apollo 9 and 10 were test flights that brought the program to the brink of the moon landing. Apollo 9 tested the lunar module in Earth orbit. Apollo 10 carried the lunar module all the way to the moon and descended to within about 15 kilometers of the surface, a full dress rehearsal for the landing. The astronauts of Apollo 10 could see their planned landing site passing beneath them, but were not allowed to land. That honor would belong to the next mission. Apollo 11 launched on July 16, 1969, carrying 3 astronauts, Mission Commander Neil Armstrong, Lunar Module Pilot Buzz Aldrin, and Command Module Pilot Michael Collins. 4 days later, on July 20, Armstrong and Aldrin separated the lunar module, named Eagle, from the command module, named Columbia, and began their descent to the surface of the moon. Collins remained alone in the command module, orbiting overhead. The descent was not smooth. As Eagle descended, alarms began sounding in the cockpit. The onboard computer was overloaded with data and was displaying error codes. Armstrong and Aldrin did not know whether to abort. In Mission Control in Houston, a 26-year-old engineer named Steve Bales had to make a split-second decision. He determined that the alarms were non-critical and gave the call to continue the descent. It was one of the most important decisions in the history of human exploration, made by a young man in a room full of nervous engineers. As Eagle approached the surface, Armstrong looked out the window and saw that the planned landing site was strewn with boulders. Large boulders. He took manual control of the spacecraft and flew it horizontally over the surface, looking for a clear spot. While Aldrin called out altitude and velocity readings, fuel was running critically low. Mission Control watched the telemetry in tense silence. When Eagle finally set down, there were only about 25 seconds of fuel remaining. Armstrong's voice crackled over the radio. "Houston. Tranquility Base here. The Eagle has landed." In Mission Control, the tension broke. Charlie Duke, the capsule communicator, replied, "Roger. Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We are breathing again." 6.5 hours later, at 10:56 p.m. Eastern Time on July 20th, 1969, Neil Armstrong climbed down the ladder of the lunar module and placed his left foot on the surface of the moon. "That is one small step for man," he said. "One giant leap for mankind." It is perhaps the most famous sentence in the English language. And in that moment, a dream as old as humanity, the dream of walking on another world, became reality. Armstrong was soon joined by Aldrin, and together they spent about 2.5 hours on the lunar surface. They planted an American flag. They set up scientific instruments. They collected rock and soil samples. They took photographs. They bounced and hopped across the surface in the moon's 1/6 gravity, discovering that a kind of loping stride was the most efficient way to move. And they looked up and saw the Earth in the sky above them, a blue marble no bigger than their thumb held at arm's length. There is a lesser-known story about the Apollo 11 moon landing that I find deeply moving. Before Aldrin climbed down the ladder to join Armstrong on the surface, he quietly performed a communion service inside the lunar module. He had brought a small vial of wine, a wafer, and a miniature chalice from his church. In the silence of the moon, in the most remote and lonely place any human had ever been, Buzz Aldrin gave thanks. He did not broadcast it. NASA had asked him not to, because of a lawsuit from atheist activist Madalyn Murray O'Hair regarding religious activities by astronauts. So, Aldrin performed his private ceremony in silence, a moment of spiritual reflection on the surface of another world. Meanwhile, Michael Collins orbited alone in the command module, further from any other human being than anyone had ever been. When his orbit took him behind the moon, he was completely cut off from radio contact with both his crewmates on the surface and mission control on Earth. He was, for those minutes behind the moon, the most isolated person in history. Collins later wrote that he did not feel lonely. He felt awareness, anticipation, satisfaction, confidence, almost exultation. He knew that he was part of something monumental. After Apollo 11, the Apollo program continued with 5 more successful moon landings. Apollo 12 made a precision landing near the Surveyor 3 probe, which had landed on the moon 2 years earlier. The astronauts walked over to Surveyor 3, removed some of its parts, and brought them back to Earth for study, to see how they had been affected by years of exposure to the lunar environment. Apollo 14, 15, 16, and 17 each explored different regions of the moon, spending increasingly longer periods on the surface, and traveling further from the landing site using a lunar rover. An electric car that the astronauts drove across the moon's surface. But it was Apollo 13, in April 1970, that produced perhaps the most gripping story of the entire program. Apollo 13 was supposed to be the third moon landing. But on April 13, 2 days into the mission, and about 322,000 kilometers from Earth, an oxygen tank in the service module exploded. The crew, Jim Lovell, Jack Swigert, and Fred Heise, heard a loud bang and felt the spacecraft shudder. Swigert radioed Mission Control with a message that would become one of the most famous transmissions in history. "Houston, we've had a problem." The explosion crippled the command module. 2 of its 3 fuel cells failed, and the oxygen supply was leaking rapidly into space. The crew could see a gas venting from the side of the spacecraft, a cloud of oxygen drifting away against the stars. The command module was dying. The planned moon landing was immediately aborted. The only goal now was to get the crew home alive. The crew moved into the lunar module, a spacecraft designed for 2 people for 2 days, now being asked to support 3 people for 4 days. Power had to be conserved to the absolute minimum. The temperature inside the spacecraft dropped to near freezing. Water was rationed to about 6 ounces per person per day, 1/5 the normal amount. The crew shivered in the cold, dehydrated and exhausted, as they swung around the moon and began the long coast back to Earth. One of the most critical challenges was carbon dioxide removal. The crew's breathing was producing carbon dioxide faster than the lunar module's lithium hydroxide canisters could absorb it. Carbon dioxide levels in the cabin were rising to dangerous levels. The command module had additional canisters, but they were square, and the lunar module's system used round ones. They would not fit. In mission control, engineers had to figure out how to fit a square peg into a round hole, using only materials available to the crew on the spacecraft. They came up with a solution using cardboard, plastic bags, and duct tape, and talked the crew through building the improvised adapter. It worked. Carbon dioxide levels dropped back to safe levels. It was a triumph of engineering improvisation. After 4 harrowing days, Apollo 13 reached Earth. The crew transferred back into the command module for re-entry, jettisoned the damaged service module, and jettisoned the lunar module that had been their lifeboat. As the command module plunged into the atmosphere, there was an unusually long blackout period, during which radio signals were blocked by the plasma generated by the intense heat of re-entry. Mission Control waited. Seconds ticked by. The blackout lasted longer than expected. Was the heat shield intact? Had the explosion damaged the command module more than they realized? And then, the radio crackled back to life. The crew was safe. The parachutes deployed. Apollo 13 splashed down in the Pacific Ocean. All 3 astronauts survived. Apollo 13 is sometimes called a successful failure. It failed in its mission to land on the moon. But it succeeded, brilliantly, in bringing its crew home alive against seemingly impossible odds. It was a testament to the skill, creativity, and sheer determination of the astronauts and the thousands of people supporting them from the ground. The last humans to walk on the moon were Gene Cernan and Harrison Schmitt on the Apollo 17 mission in December 1972. As Cernan climbed back up the ladder of the lunar module for the last time, he spoke words that still carry a weight of melancholy. America's challenge of today has forged man's destiny of tomorrow. As we leave the moon at Taurus Littrow, we leave as we came, and, God willing, as we shall return, with peace and hope for all mankind.